Okay, so hello everyone and welcome to the IIIT Delhi Topology and Geometry Seminar. So it's my pleasure to welcome Oscar Cosserat to the from Göttingen University to continue his lecture series on invariant theory of Hamiltonian mechanics and related numerical analysis. Today, it's his second talk of the series, and he will be talking on symplectic groupoids and Hamiltonian-Jacobi equation. So, over to Oscar.
Yes, thank you. So let me sum up the message of the last lecture. In the last lecture, we defined Poisson manifolds and Hamiltonian systems on Poisson manifolds. So Hamiltonian systems are dynamical systems, so smooth vector fields that you can integrate to get a flow and a trajectory on the manifold. And these systems, these dynamical systems, admit symmetries, more precisely, preserved quantities that are given by the symplectic foliation. So remember that a Poisson manifold is foliated into symplectic leaves. It means that any Poisson manifold is partitioned into some manifolds with a different topology than the one of the ambient manifold. But each of these manifolds coming from the partition admits a natural symplectic structure coming from the Poisson structure of the ambient space. And Hamiltonian flows remain on this symplectic foliation, on this symplectic leaf all along the trajectory. Means that Hamiltonian flow starting from x0 for x0 some point of M, the Poisson manifold, the trajectory will stay on the symplectic leaf of x0 at every time. And what we have seen last time is that if you want to approximate these Hamiltonian trajectories, if you want to do some numerical analysis to compute these Hamiltonian flows, traditional methods do not preserve the symplectic foliation and do not extend straightforwardly from traditional numerical analysis to the context of Poisson manifolds. And these Hamiltonian systems are important in mechanics. So I gave examples last time. Some examples are from astrophysics, from celestial mechanics, but also from, there are also examples from chemistry, for instance, or control theory. And so it matters to be able to develop some numerical tools that provide an approximation of these Hamiltonian trajectories, which is nice, which has appropriate properties. And in particular, it's important to have some numerical tools in this context that preserve the symplectic foliation. So this is what we look for. We look for numerical tools that preserve every leaf of the symplectic foliation. In other words, we look for numerical methods such that the trajectory follows the one of a Hamiltonian trajectory. And this Hamiltonian trajectory will be close to the Hamiltonian trajectory we want to approximate. So all of this requires some more sophisticated mathematical tools than the one usually used by researchers in numerical analysis. And this is what we're gonna do today. So today we're gonna develop some mathematical notions that are a bit more intricate than usual tools you may encounter in numerical analysis. So objects such as groupoids, for instance. And we will explain tomorrow how to use these groupoids to make some numerical methods that verify satisfying properties in the context of Hamiltonian systems for Poisson structures. So this is a program of today, is to introduce first groupoids, then symplectic groupoids, and the relation between symplectic groupoids and Poisson manifolds. I will mention also Lagrangian bisections and bi-realisations. And the Hamilton-Jacobi equation is a proper tool we will use in 1 week to construct these Hamiltonian Poisson integrators. So let us start. We start with the definition of a groupoid. So a groupoid is a set G over a set M with two maps alpha and beta, a product which is written with this dot, an identity section I, and an inverse, verifying some conditions. So let me explain what is a groupoid. You should think about a groupoid as a space of arrows between various points. So G is a set of arrows, and M is said to be the object, or also sometimes the set of base points, because if G is a space of arrows, then M will be given by starting and ending points of arrows. So groupoid is as follows. If you have A, B, C, and D in M, and then if G1 is an arrow between A and B, and G2 is an arrow between B and C, then groupoid axioms tells you that you can compose the arrow G1 with the arrow G2 such that you obtain an arrow starting at B and ending at C. Which will be G1 dot G2. And then there are these source and target maps. So the source of G1 will be A, the target of G1 will be B, the source of G2 will be B, the target of G2 will be C, and the target of G1 times G2 will be the target of G2, and the source of G1 times G2 will be the source of G1. It's very natural if you think about the groupoid as arrows and ending and starting points. So here I pictured 3 arrows, right? One between, so the arrow G1, the arrow G2, and the arrow G3, because there is an associativity condition telling you that you can compose first G1 with G2 and then G1.G2 compose with G3, or you can also compose G2 with G3 and then left compose G2 times G3 with G1, and this is equal. So this associativity condition is very natural because the composition of maps in general is associative. Let me tell you what the identity section is. The identity section is a map going from the base set to the set of arrows, and it sends a point to the arrow going from this point to itself. So if this is M, the point M, then this arrow is I of M. And those equations tell you that you can compose to the left or to the right the identity arrow to any other arrow, and it doesn't change the arrow. So it acts as the identity arrow for the composition of groupoids. And the axiom for the fourth axiom is about the invertibility of arrows. So it's very important that in a groupoid, you can always invert an arrow, meaning that, for instance, G1 here provide an arrow going from B to A, which is G1 minus 1. If you like...
Oscar?
Yes.
So in the 2.1, you alpha G dot H is alpha G. Should it be alpha of G?
Yes, you're right. Sorry about this. Yes.
Yeah, and like just a comment, like this groupoid can over a set can be like we can see that as just a category, like then this operation dot is just the composition of arrows in the morphism sets.
Yes, exactly. That's a good point. I was about to make this remark actually.
Okay. Yes,
Yeah, that's accurate. So you may also define a groupoid as a small category with invertible arrows. So a small category is a category such that the objects are sets. And you ask invertibility of the morphisms. So this is axiom 4. Right, exactly. But for us, everything will be a set. We don't need any category for this lecture. Although it's the right point of view. The right point of view for a groupoid is one of category. Exactly. So remember that the Poisson manifolds we care about are smooth in this lecture. So let me explain what the smooth setting for groupoid is. So the groupoids we care about in this lecture are called Lie groupoids. So a Lie groupoid is a groupoid G over M, such that G and M are smooth manifolds. The product and the identity section are smooth maps. And the source and targets are smooth submersions. So I wrote this remark because indeed the topology of groupoids is intricate in general. First, the space of arrows. So there are interesting examples where the space of arrows is not Hausdorff separable. And also some of the smoothness properties of the structure maps you may prove. So this is enough to ask for a Lie groupoid, but then you can prove out of this, for instance, that the inverse is also smooth, etc. So this lecture is not about the topology of groupoids, but the topology of groupoids would be actually one lecture. But the short message of this slide is that, well, for us, a Lie groupoid will be a groupoid with structure maps that are smooth, roughly speaking. Let me give you examples. So, what are examples of Lie groupoids? So we need one base set, one base manifold, and we need a space of arrows. So if you pick a manifold M, smooth manifold M, you can always construct the pair groupoid of this manifold, which is one of the most basic examples of groupoid. So it works as follows. For every pair of points x, y in M, there is one arrow going from x to y. Okay, so this tells you that G is over M, of course. And then the product of the groupoid is, of course, well, the composition of arrows. So xy times yz is xz. The identity section of X is given by the doublet XX, and the inverse XY minus 1. So maybe someone among you can try to guess what is the inverse arrow of XY.
It'll be YX.
Yes, that's a win. YX. All right. The second example is slightly less trivial. It's called the action groupoid. So M is a smooth manifold again, and G is a Lie group acting on M, such that the action is smooth. Then so G is over M again, and now arrows are given by the orbits of the group. Right, so the arrow given by G X actually goes from X to Gx. And you can compose those arrows by composing by this composition rule. So, but be aware that you can compose the first arrow with the second one. So you can compose Gx with H, G times X, only because you start at Gx. So you see that in a groupoid in general, you can compose two arrows only if the second one starts where the first one ends. So here, of course, the composition is given by the composition of the Lie group, but you must be careful to start at the right point. So the identity section is provided by the identity of the group, because the identity, it follows from the axioms of a group action that the neutral element of a Lie group acts as trivially. And let me mention the third example, which is a particular case of the second example, when the action is given by the co-adjoint action of the Lie group on the dual of the Lie algebra. So the third example is exactly the specific case of the second example. So remember that what we want to do is to construct approximations of Hamiltonian systems that preserve the symplectic foliation of the Poisson manifold. And we are interested in Lie groupoids because precisely they allow to deal with singular foliations on the base. It is a theorem that any Lie groupoid G over M induces a partition of the base M. So actually this statement is true even if the groupoid is a set. You don't need any smoothness assumption for G to induce a partition of the base M. This would be true even if M is a set. It turns out that in the Lie groupoid setting, this partition is a singular foliation. In particular, each leaf is an immersed submanifold. So this equivalence relation induces a singular foliation on M. And we had three examples of groupoids that we just saw. So let us detail what this foliation is for our three examples. So a leaf will be given by the leaf of x if x is in M, if x is on the base, and the leaf f x of M will be given by all the points you can reach by following arrows of the groupoids starting at x. So remember that for our basic first example of a Lie groupoid, which was a pair groupoid, we decided that there is an arrow going from any point of M to any other point of M, meaning that the foliation of a pair groupoid has only one leaf, which is the manifold itself. For our slightly less trivial example of the action groupoid, the foliation is made of the orbits of the action, because that's what our arrows are. And if we specify again the second example to the example of coadjuvant action, then the foliation of G times G star over G star is made of the coadjuvant orbit. We will also need a notion of bisection. So let me come back 1 second to the induced singular foliation. So that was at one point x of M, we could picture the leaf of x. Now we will find a way to go. We will find a way to go everywhere from a point to other places of the leaf, and this is given by bisection. So bisection is a submanifold L of G such that the restriction of the source to L and the restriction of the target to L are diffeomorphisms. It means that you can invert them. So let me give you one picture of bisection. You may think about the base embedded in the groupoid G, right? You can always embed M into G using the identity section, and then the submanifold L of G will be a bisection if you can invert alpha and beta restricted to L. So this is L. And you have two ways of projecting L on M. So this is alpha of P and beta of P. If P is a point, is an arrow in the groupoid. And you can multiply those bisections using the groupoid law of the bisection. And what matters for us is that any bisection L induces a diffeomorphism that we denote phi L, such that phi L remains on one leaf. It means that X and phi L of X belong to the same leaf induced by the groupoid. So what is phi L? Actually, if you take the picture I just made above, so phi L, so this is the bisection L. So this is alpha minus 1, well, alpha restricted to L minus 1, because we assumed that the source restricted to the bisection is invertible. And then you project using the target. And this is phi L. So if X is here, then this is phi L of X, which is this point. And this diffeomorphism remains on the leaf it started on. So we get closer to our task. Our task is to approximate some dynamical system by remaining on the same leaf of the symplectic foliation. And now we start understanding much better how to deal with this foliation. But for now, we don't have any symplecticity for this foliation. And in order for the foliation of a Lie groupoid to be symplectic, we need a notion of symplecticity for this groupoid. And this is what I explain right now. So, definition of a symplectic groupoid. A symplectic groupoid is a Lie groupoid, G over M, such that G is equipped with a symplectic form omega with this equation, where M is the product and PR1 and 2 are the projection on the first and second factor of G times G, respectively. Right, so a bit of terminology. Omega is said to be multiplicative. And if you don't want to take this definition too seriously, there is a rough way to write the multiplicativity. So this equation is wrong, strictly speaking, because you may notice that omega of G times H and omega of G and omega of H do not belong to the same vector space, right? Omega is a two form, so omega G, omega H and omega G times H do not belong to the same space, although this, well, may be useful to remember this equation sometimes if you want to do some computation. This remark is another way to define a symplectic groupoid. So it's another way to explain this equation. You may write that m star of omega minus PR1 star of omega minus PR2 star of omega equals 0, which is exactly the same equation. And this equation might be reformulated as the isotropy of the symplectic form on G times G bar equipped with the symplectic form omega on the first factor, omega on the second factor, and minus omega on the third factor. So the graph of the product of the symplectic, the graph of the groupoid product is indeed inside G times G bar. And if you restrict the symplectic form to the graph of the product, the vanishing of this form given by omega minus omega is equivalent to this equation.
So here G bar just means the I of G. Like inverse of the G, the arrows are reversed, all the arrows.
No, the arrows are not inverted, but the symplectic form is taken to be minus
Okay.
the one on G, but the arrows remain the same.
Okay.
Yeah.
And another thing is like here when I'm in the equation, when you are saying m star of omega, that's land in the like like a subset of G cross G.
Yes.
And on the other side, you have the honest forms in the in G cross G. So you kind of again pull that back to see that in G upper 2 kind of thing. Like kind of forms, both the side forms are in different kind of spaces. So that's
yes, good point. So maybe it's more accurate to write G2 here, because then it's the same space.
Yeah. Then it's fine. Yeah, correct.
Let me state some properties. So we identify M with the image of the identity section. Then M is Lagrangian in G. So what does it mean? So Lagrangian submanifolds are actually important in this lecture. It means that if you restrict, it means two things. First, if you restrict omega to M, and this is 0. And so this would mean that M is isotropic. And a Lagrangian submanifold of a symplectic manifold is defined to be maximally isotropic meaning that the dimension of M is the dimension of G over 2. Cannot be bigger than this because omega is non-degenerate. So isotropic. It follows from linear algebra that isotropic subspaces of omega are at most of dimension half of the dimension of G. So for instance, typically this first proposition, you can prove, you can roughly prove with the equality, the rough equality I gave you on the last slide, because let me take more space. If you take omega of I of M, this will be omega of I of M square, because the identity arrow you can compose and it doesn't change. Like I of M is equal to I of M square. And now you use the multiplicativity to obtain that it is omega of I of M but twice, right? Because omega, if you follow this rough equation I gave you, omega of I of M square is equal to omega of I of M plus omega of I of M, which is 2 times omega of I of M. And so omega restricted to I of M must be 0. The inverse map is an anti-symplectomorphism. So this is also interesting because it tells the relation between the product of the symplectic groupoid with the symplectic form again. What can I say about this third point? The fibers of the source are symplectically orthogonal to the fibers of the target. Well, so the third point is useful to prove the fourth point, which is that there is a unique Poisson structure pi on M such that the source map alpha is a Poisson map and the target map beta is an anti-Poisson map. And then the groupoid G over M is said to be integrating M pi. So G over M here is understood as coming with its symplectic structure. So maybe it's more accurate to write G over M with omega. Right, so because the symplectic structure was needed in the third point. So this omega provides Poisson brackets for this equation. Here the Poisson brackets are for omega. Remember for the last lectures that if you have a symplectic manifold, you automatically have Poisson brackets on these manifolds. So here the Poisson bracket I consider are the one of omega. I finish with this informal remark. The symplectic groupoid desingularizes the symplectic foliation on the base. So it's also So let me keep this as an informal remark for now. So we have seen in the first lecture that the symplectic foliation of a Poisson manifold was singular, meaning that there are leaves that are very close to each other, but such that the topology of two neighboring leaves might be very different. So the symplectic foliation is something that is very much singular, whereas a symplectic groupoid is much more regular in the sense that alpha and beta are submersions. So now we learned that you may recover the foliation by this alpha and beta. Keep in mind this picture. This alpha and beta. That are two projections from G to M. And these alpha and beta are submersions, so they are much more regular objects than the symplectic foliation we started with. Also, you may notice so what are we doing right now? So at the first lecture, we considered a Poisson manifold, and we realized that we could not deal with the symplectic foliation with like traditional mathematical objects. So what we did was to stop thinking about Poisson manifolds. We managed to define and study symplectic groupoids. And then we realized that out of a symplectic groupoid, you can recover a Poisson manifold. And once you have the symplectic groupoid, you can study in an efficient way the symplectic foliation of the Poisson manifold. So it's not like we started from a Poisson manifold, we then constructed a symplectic groupoid for this Poisson manifold, and we managed to understand the symplectic foliation. It's more like we defined another object that a priori was maybe not related to Poisson manifold, and at the end, this allows to study what we started with at the end. So this is the goal of a symplectic groupoid. This is a few examples. So the cotangent bundle T star M of any manifold M equipped with a canonical symplectic form and T star M and source and target equals the cotangent projection integrates a zero Poisson structure on M. So what does it mean? It means that the set of objects is M, and source and target are equal. They equal the cotangent projection. And then what is the product? The product is given by the addition on every fiber. So for all P1, P2 in T star M, P1 dot P2, dot is our notation for the groupoid product, remember? Well, this is P1 times P2. So of course, for this, you need P1 and P2 to be over the same base points, meaning that if tau is the cotangent projection of T star M, then tau of P1 equal tau of P2. So this is our first example. So every symplectic groupoid induces a Poisson structure on the base. So here we define a symplectic groupoid structure on T star M, and the induced Poisson structure on M is the zero Poisson structure. Now if M is a symplectic manifold, so a symplectic manifold is also a Poisson manifold with Poisson brackets given by the symplectic form. And this symplectic manifold, this Poisson manifold given by the symplectic form is integrated by the pair groupoid M times M bar, where M bar is again equipped with minus the symplectic form of M. So in a more rigorous way, you may write this as PR1 star of omega minus PR2 star of omega. And this gives the symplectic form on G. Remember that we had this action groupoid as an example of a Lie groupoid. And this action groupoid has a cotangent bundle structure. And every cotangent bundle has a symplectic form, a canonical symplectic form. And this symplectic form is compatible with the Lie groupoid structure of the provided by the action by the cotangent by the coadjuvant action, such as at the end the action groupoid T star G equipped with the canonical symplectic form and T star G integrates G star. So G star, remember that G star carries a canonical Poisson structure, which is linear. So this is something we mentioned in the last lecture. There is also an example. So in the first lecture, we had some quadratic Poisson bracket xi bracket xj that is called a I j. Aij, xi, xj. Those are called cluster Poisson structures, and a symplectic groupoid integrating this cluster Poisson structure has been computed in the literature. So be aware that in general it's not so easy. In general, it's a hard task to compute a symplectic groupoid that integrates a given Poisson structure. So there is plenty of work in the literature trying to use deformation theory. For instance, I will probably speak about this a bit at the end of the next lecture in 1 week. You may try to use deformation theory to try to construct symplectic groupoids integrating a given Poisson structure, but in general, we know how to do this for a class of examples, for several classes of examples, but the general procedure to compute a symplectic groupoid for a given Poisson structure is not known. Remains some open problem, at least to compute it explicitly. I may also mention that there are obstructions for a Poisson manifold to be integrated by a global symplectic groupoid. What you may look for is called a local symplectic groupoid. This is something I will maybe talk about maybe in a few, maybe today or maybe next week. So we had a notion of bisections for Lie groupoids. And remember that these bisections of Lie groupoids allowed us to construct some diffeomorphism on the base that were preserving every leaf of the foliation induced by the Lie groupoid. Now we know that if we have a symplectic groupoid, this foliation is symplectic, meaning that every leaf has a symplectic structure. The question is how to pick my bisection such that the diffeomorphism I get on the base preserve the Poisson structure, right? It's a natural question. So let us start with a symplectic groupoid, G omega over M. So the right notion of bisection to get Poisson diffeomorphism on the base is called Lagrangian bisection. Definition: a Lagrangian bisection is a bisection which is Lagrangian as a submanifold of G omega. And I mentioned this group product of the group of bisection. So the same way you can multiply bisections, you can multiply Lagrangian bisections. It works the same. And this group of Lagrangian bisections acts on G by symplectomorphisms. So all of these are technical lemmas to prove this important theorem. So let us assume that the fibers of alpha are source connected. This will be useful for us. So here is the theorem. This theorem is known probably from about 30 years now. It's probably from 1987. So probably the first one that understood this is Weinstein and his co-authors. So let L be a Lagrangian bisection. Then the induced diffeomorphism phi L is a Poisson diffeomorphism on the base and stays on a leaf. So the second point is not a surprise because a Lagrangian bisection is in particular a bisection. So the diffeomorphism phi L stays on a leaf because it comes from a bisection. But now the fact that L is Lagrangian provides this additional feature, which is that the diffeomorphism is a Poisson diffeomorphism. So now we remember from the first lecture that Hamiltonian flow on the base M, right? If M is a Poisson manifold and H a smooth function, then phi th the flow of H at time t. So we remember that it stays on a leaf and it preserves the Poisson structure. So phi th is a Poisson diffeomorphism that stays on the leaf it started on. So we are getting closer to our goal, which is the following question. For any Hamiltonian and T some time where the Hamiltonian flow is well defined at this point, which Lagrangian bisection L recovers the Hamiltonian flow phi t of H, namely how to choose L such that the induced diffeomorphism by L is given by phi th. And this is by answering to this question that we will construct some numerical methods for Poisson Hamiltonian systems, actually. But I will probably, so today until the end of this lecture, I will keep giving the mathematical tools to achieve this task, and the numerical simulations and the integrators and the numerical methods I will give next week. So to answer the question I just raised, it's actually nice to put this symplectic groupoid in a more convenient space by using the Weinstein tubular neighborhood theorem. So this Weinstein is the same one as the one I just stated. So Weinstein is one of the main contributors when it comes to symplectic groupoids. So theorem, there exists a symplectomorphism from an open neighborhood of M in G, M seen as embedded in G, onto an open neighborhood of the zero section of T star M. What does it mean? It means that if you keep in mind this picture of the symplectic groupoid, if G is the ambient space and M is some embedded submanifold inside G, then if you're close enough to the identity section, so if you pick a tubular neighborhood, which is what I picture right now, then you may identify G with T star M. So there is a small intuition about why is this possible. For instance, you remember that the dimension of G equals twice the dimension of M. Meaning that, for instance, as submanifolds, as manifolds, at least locally around a point, you can find such a diffeomorphism. It turns out you can do this along the whole of M. So this is what this tubular neighborhood theorem states. So one can transport any local symplectic groupoid towards a neighborhood of the identity section inside the cotangent bundle of the base. And there the symplectic form is known. It's known because the symplectic form of G becomes the canonical symplectic form of T star M. And this provides many Lagrangian bisections thanks to the following remark. So any closed one form on M provides a Lagrangian submanifold of T star M. And locally, any image of a sufficiently small closed one form is a Lagrangian bisection. So it's a fact of symplectic geometry that if you pick, say, psi one form on M, such that d psi equals 0, then so psi is a map from M to T star M, right? It's one form. And so psi of M is inside T star M. And the closeness of psi is equivalent to the fact that psi of M is a Lagrangian submanifold of T star M for the canonical symplectic form on T star M. So this second point is that we ask psi to be a sufficiently small one form, because what may happen if psi is too big is that psi of M is outside G. Remember that now G is a tubular neighborhood of the zero section of T star M. So the zero section of the cotangent bundle is now the identity section of the symplectic groupoid. And if psi is a sufficiently small closed one form, then its image will be in G, G being itself in T star M. So for instance, as an example, you may pick the psi as a 0, one form, like the one form being equally the 0, and then you will recover the embedding of I. Right, the identity section is given by the 0, 1 form. And any perturbation of this 0 section, if the perturbation is given by a closed one form, which is small, this will provide a Lagrangian bisection. So now let us axiomatize this. A bi-realization is a bi-realization of a Poisson manifold M pi is a triple G alpha beta such that G inside T star M is a neighborhood of the zero section. Alpha and beta are the source and target. There are smooth submersions just like in the symplectic groupoid setting, such that alpha of the identity arrow and beta of the identity arrow are the identity. So those are reminiscent of the fact that alpha, like the source of the identity arrow and the target of the identity arrow, are just the base point of the identity arrow. Alpha and beta are respectively Poisson and anti-Poisson morphism for the canonical Poisson bracket on G. And for all f and g smooth functions on M, alpha star of A, F, and bracket with beta star of G equals 0. So these items 2 and 3 allow to reconstruct the product of the symplectic groupoid, actually. But you may think about this bi-realization definition as just a symplectic groupoid for which we found a tubular neighborhood theorem. So a bi-realization is a local symplectic groupoid transformed by Weinstein tubular neighborhood theorem. So these are examples of bi-realizations. So what is nice with bi-realizations is that it's a bit easier to compute with bi-realizations than with symplectic groupoids, because in a bi-realization, we know the space of arrows. So the space of arrows in a bi-realization is always a subspace of the cotangent bundle of the base. And in practice, it's much easier to compute with. And remember, that's what we want to do. At the end, we want to compute Hamiltonian dynamics. So these are the 3 examples of the first lectures. So we had 3 examples of Poisson structures in the first lecture. We had the symplectic Poisson structure. So here I pick Darboux coordinates, as you may remember. And those are formulas for a bi-realization for this canonical Poisson structure on T star R. Our second example of Poisson structure was something that was called Lie Poisson structure. So this is a bi-realization for the Lie Poisson structure on SON star that I identified with SON using the Frobenius metric. So the Frobenius metric is given by the trace. Maybe with 1/2 here. The 1/2 doesn't matter. And the third example is the example of cluster Poisson brackets. So remember that I mentioned that in the literature, someone computed the symplectic groupoid of the cluster Poisson bracket, Lee and Ruppel, a few years ago. So this allows us to compute the bi-realization for the cluster Poisson bracket. But in general, the computation of a bi-realization for a generic Poisson structure is a hard task for the same reason that the computation of a symplectic groupoid is a hard task. In general, it's not so easy to find such alpha and beta. So this is a short sum up about bi-realisations. A few insights maybe. Bi-realisations is symplectic groupoid computations. So this first remark is that G is inside T star M, and the symplectic form on G is the one of the canonical symplectic form on T star M. And this provides nice points. So cotangent lifts of Poisson automorphisms are morphisms of local symplectic groupoids. If you don't understand all the words of this sentence, it's all right. It's just to say that isomorphisms of symplectic groupoids are easier to compute if you deal with bi-realisations. Lagrangian bisections are images of closed one forms. This we have seen recently. And smooth families of Lagrangian bisections are smooth families of closed one forms. This we will answer with the this will be the crucial remark to answer the questions of the Hamiltonian flows that we asked before. So now let us pick a Hamiltonian, and we ask this question again: which Lagrangian bisection induces the flow of H as diffeomorphism on the base? And well, first point of this theorem. So this Hamilton-Jacobi equation admits a unique solution ST for T in a neighborhood of 0. And ST is the Hamilton-Jacobi transform of H. This is just a terminology. The important point is the second one. Such a solution allows to compute the flow of H by this formula. So the second point means that the induced diffeomorphism given by the bisection associated to dST is the flow of H. So dST is a closed one form on M. And the induced diffeomorphism on the base is the flow of H. Now it turns out that this approximation of like an approximation of the solution of the Hamilton-Jacobi equation provides Hamiltonian Poisson integrators at order I and time step delta t for the Hamiltonian flow of H, meaning that a solution of the Hamilton-Jacobi equation at order I provides an approximation induced as diffeomorphism, an approximation of the Hamiltonian flow at order I, such that this approximation also follows the trajectory of a Hamiltonian. So this terminology is detailed here. So this I finished, some exercises for next week, and here is some bibliography. So I'm done for today.
Thank you, Oscar. Thank you for the nice talk. So are there any questions from audience?
So, but I don't think there is much people in the audience, actually.
Oh, okay, yeah. Yes, Sachin is there. Okay. So I have just a couple of just clarification probably. So in the where you define the action, the like group action, groupoid kind of thing, G and X.
The groupoid action, the
Yeah,
action.
yeah, just the in the beginning of the just before that. Yeah, even before this one. Yeah, here. Go back to the next thing. Yeah, in the second thing, like whether this the dot is gx with h g dot x, should this be hgx or ghx?
So you want,
Yeah, because the starting point is x, so it's going to the h dot g dot x, which is hgx.
you want hg instead of gh?
Yes, yeah, I think so.
Yes. Because yes, you're right. Okay, thank you.
Yes. So and next, like I don't know if I understood it correctly. Like in the last lecture, you said like if we have symplectic manifold, then the symplectic form is gives the Poisson structure, the bracket it generates. So here you instead you here like in the groupoid setting you also started with a symplectic groupoid, and from there you said like there is a unique Poisson structure on the base, which kind of integrate that symplectic groupoid, right?
Right. So this is in the properties.
Yeah. Yeah. So, this okay, not this one. So you somewhere you said like there is a unique Poisson structure for a given, like if you start with a symplectic groupoid, then there is a unique Poisson structure uh, giving this to the like source and target thing. Yeah, here only. Yeah, the fourth example. Yeah, correct. Yeah. So, the opposite thing, is it true? Like if we start with a Poisson structure, then is it possible to give a symplectic groupoid kind of thing? Like the same question kind of true for the manifold setting itself.
Can you repeat? So if you start with the Poisson structure?
Poisson structure, so is that give rise to some symplectic groupoid structure?
So your question is if there is if I have a Poisson manifold, can I find a symplectic groupoid?
Yeah, kind of, yeah.
Right. So no. What is always true is that you can find a local symplectic groupoid integrating this Poisson structure.
Yeah. That's what you said in the some like in the this Weinstein neighborhood theorem kind of thing. You kind of integrated locally.
Yes, exactly. So the main feature of local symplectic groupoids compared to symplectic groupoids is that you cannot, well, you can multiply an arrow with another arrow if, of course, the source and target correspond, but also if one of the arrows is sufficiently close to the identity arrow.
Right. Okay.
Right. And so, but the obstruction for a Poisson structure to be integrated by a global symplectic groupoid is
Right.
known. And for instance, it's related to the properties of the symplectic foliation. So if the symplectic foliation is very regular, for instance, if all the leaves are similar, if then it will be okay. But if the symplectic area varies a lot from one leaf to another one, then you will have issues to integrate this Poisson structure. It's actually it's not something you can explain in 5 minutes, but if I had to explain it in one sentence, it would be this. You can, once you have a symplectic form, it's a two form, so you can integrate on surfaces. So now you pick a sphere around a point. Using this symplectic form, you can get a number by integrating the sphere over by integrating the symplectic form over the sphere. And now if you make this sphere varying in the transverse direction of the foliation, going from one leaf to another, if this number that you get by integrating the sphere in the transverse direction varies a lot, then you will have issues for the integration of your Poisson structure of a symplectic groupoid. So the geometric obstruction is quite well understood for maybe 20 years now, a bit more.
So also you last class you said like the homotopy type of the leaves actually varies very rapidly kind of thing, like they may vary very drastically from one to the other. Like if we have kind of something like all the leaves are homotopy type same, then is it possible like is that what you are mean by similar leaves?
Yes. Well, so so the example I gave about singular leaf is if R3 is foliated into spheres, and then one sphere, well, one leaf in the origin is given by just a point, and then all the leaves around are two-dimensional spheres, whereas the leaf at the origin is zero-dimensional. So this is in R3.
Right, yeah.
That was an example of a singular foliation. Yeah, it's also related to the homotopy type of leaves, indeed. That's also a huge topic, the topic of normal forms around a leaf of singular foliation. So it is an active research topic. If you have a singular foliation, to determine if the leaves around a particular leaves are similar or not to the leaf you look at. And it's related to periodic orbits of dynamical systems also.
Okay.
Yes, if you have a periodic orbit, well, if you look at the Poincaré section, it's a question to understand if you start from a point which is close to this periodic orbit, will your orbit also be periodic, etc. Is the dynamic chaotic around? This is related to singular foliations also. Because in this case, the leaf is one-dimensional, it's just an orbit, but when you deal with singular foliations, you care about similar questions, but with bigger leaves in terms of dimension.
Okay. Thank you. So another question.
Okay, you can go ahead.
Okay, so I last like kind of there the question you asked like if we have a bisection then and a Lagrangian Hamiltonian you have, then one side you have the at a fixed time you have phi T the flow automorphism and kind of the capital T of L corresponding to the bisection. Whether those two are like given Hamiltonian, we have whether such L or not. Like the
Yes.
other direction I missed probably like other direction is true kind of like if I start with a bisection can I construct the Hamiltonian?
Yes. It depends on if your so it will be true if your Lagrangian bisection is the graph of an exact one form.
Oh, okay. I see.
If your bisection is the graph of an exact one form, then you can find a Hamiltonian such that the induced diffeomorphism is a graph.
Like is that something related to the like vanishing of the second cohomology thing? Like if the second cohomology vanishes, then all the closed forms are exact. And
to the Durham cohomology of M?
Yeah, Durham cohomology of M.
Yes, but maybe more like the first group, probably, because if you have a Lagrangian bisection, you can find some closed form such that this Lagrangian bisection is the image by the closed form of M.
Right.
And then the question is whether you can find some exact form.
Right.
Such that the differential of this exact form is
right.
I mean some primitive of the closed
Yeah,
form.
right. Yeah.
Yes.
Yeah. That's all I have. Yes, Sachin, if you have any question.
Hi, Oscar.
Hello, how are you?
Yeah, I'm good, not good. So yeah, I just have one question. Can you go to your Hamilton-Jacobi equation?
Yes.
Yeah, so the usual solution on manifold is the distance function, no?
Can you repeat, please?
So if M is a manifold, then the solution of the Hamilton-Jacobi equation will be the distance function. So I cannot see it here at least. So can you tell me?
So I can tell you why I called it Hamilton-Jacobi equation, because it's not, it's a bit subtle. So it's not a proper generalization of the Hamilton-Jacobi equation of of Carl Gustav Jacobi of 1842. But it's constructed following the same pattern. So the one of Jacobi was some correspondence of Lagrangian submanifolds. So I can explain you. I tell you something. So if you're on T star Q, then you have a symplectic form there. And if you have a Hamiltonian on T star Q, you have the Hamiltonian flow of H, which is a symplectomorphism of T star Q. And a symplectomorphism of T star Q is a Lagrangian submanifold of T star Q times T star Q bar. And now it turns out that this space is symplectomorphic to T star of Q times Q. So that if you send the Lagrangian submanifold of T star Q times T star Q bar given by the Hamiltonian flow of H inside T star of Q times Q, you can try to find S, ST maybe, a smooth function on Q times Q such that dSt is the Lagrangian submanifold corresponding to the Hamiltonian flow through this symplectomorphism. And the way we constructed this Hamilton-Jacobi equation follows the same pattern because we interpolate the Lagrangian bisection inducing the flow of H with the graph of dSt. So those two Hamilton-Jacobi equations are really very much related, but so I don't know exactly which Hamilton-Jacobi equation with the distance you speak about, but I'm not surprised you don't recover this straightforwardly because this Hamilton-Jacobi equation is a Hamilton-Jacobi equation in the sense of correspondence of Lagrangian submanifolds, but it's not a proper generalization of the classical Hamilton-Jacobi equation.
Okay. No, I basically was talking about the Hamilton-Jacobi equation, like the h of x du and u equals to 0 on omega and u equals to some u0 on boundary of omega. That kind of Hamilton-Jacobi equation.
With some variational principle?
That I am not sure because I have not derived it. So that I'm not sure.
Okay. But there are plenty, so there are plenty of Hamilton-Jacobi equation. I'm not saying that this is the right and unique Hamilton-Jacobi equation.
Okay. No, because like that is one I have used. So that's why I thought there may be some relation. Okay.
But so it's quite common to take as H something given by a metric on Q. So if you have a metric on Q, then T star Q and TQ are isomorphic, and you can take for H just the distance. Maybe that is what you mean. And
Yes.
and then indeed the Hamiltonian flow is given by the geodesics. So this would be, if you specify H as given by the square of the Riemannian metric, well, the square of the distance given by the Riemannian metric,
Yes.
then you will recover indeed geodesics as the Hamiltonian flow on the base. That's true.
Right. Okay. Okay. Thank you.
Oscar, I just get another just kind of query. So for suppose we have started with connected manifold, path connected manifold, then on that we actually can define a groupoid, like the groupoid for any 2 points, you just assign the smooth path between those 2 points. The homotopy class of that. So does that groupoid to do something with like this kind of in anything related, like
Yes, yes, it's related. So this is actually, it's kind of an improvement of my example of the pair groupoid.
yeah. So there you considered a unique path, but in general for manifold there may not exist only one homotopy class between 2 points. So that's
Right.
the difference. Yeah.
And if you want to integrate a Poisson manifold where the Poisson structure is given by a symplectic
Yes.
form, you may take the pair groupoid, but you may also take this path groupoid, which is actually better because it's more accurate. So there is something in a groupoid called the isotropic group. So the isotropic group above X in M will be the group of arrows starting at X and ending up at X. And this is a group. And well, you may define the accuracy of an integration as the integration with the smallest isotropy groups, because those are not inducing any foliation on the base. You don't really care about those isotropic groups. They are not relevant to describe the foliation on the base, because you don't go anywhere starting from a point and following those arrows. You would like to get rid of those. And your example has smaller isotropic group than the pair groupoid. So
Okay.
let me is it true? No, maybe it's not true. No, that's not true. But well, this path groupoid was useful for something I forgot.
Okay. Fine. We can discuss. It's already late. Sorry. We can discuss it later, next time. Okay. So thank you, Oscar, for really nice talk. So we'll meet next week then.
Yeah.
Thanks.
Okay. See you.
See you.
Yeah.